Let's talk about these brain teasers of the type complete the sequence. The way they work is somebody gives you a sequence of, say, numbers, like 1, 1, 2, 3, 5, something. And they ask you, what is the next term of the sequence? You only get like 4 or 5 terms of the sequence. And then the question is, what's the next term? This exists not just with numbers. When you have a circle and then there is a gap somewhere in the circle and this gap wanders around through various pictures. And then you have to tell like, where's the gap in the next frame, so to speak, if it were a video. Or with like arrows, like there could be 2 arrows and then one arrow is always flipping up and down and the other arrow is rotating like in 45 degrees. You just see a few of these arrows and then the question is, please draw the directions of the arrows in the next picture. And then you have to deduce that these are the movements that these arrows make. Stuff like this. And of course, it's tough for a mathematician because we know that if you just give me 4 numbers, there isn't a unique answer to what the next term is. There isn't a unique pattern. Any 4 numbers can have all sorts of patterns in them, or like 5 numbers or 6 numbers, it doesn't matter. For example, if you give me 4 numbers, I'll always find a polynomial of degree 3, which attains these numbers at the points 1, 2, 3, 4. So there's definitely always the answer like, oh, look, these are the values of a polynomial. So there's a good example if you want to tell people what the problem is in these games where supposedly there is a clear continuation of a sequence. Let me show you. 17, 19, 23, and 29. There you go. What's the next term in the sequence? And what's the pattern of these numbers? Here's one pattern, and this is probably the pattern which people are more likely to see. These are all prime numbers. So something with prime numbers. And then you realize, oh, wait. Not only are these prime numbers, these are even prime numbers in order. So this really is just the list of prime numbers, except we don't start at 2, we start at 17. So there you go, you have a perfect explanation for this sequence. Except for there's another solution. You can also write n squared minus n plus 17. If you plug in 1, 2, 3, 4, this will give you exactly these values. I plug in 1 squared is 1, minus 1 is 0, so I get 17, that works. 2 squared is 4, minus 2 is 2, 2 plus 17, that's 19. 3 squared is 9, 9 minus 3 is 6, 6 plus 17, that's precisely 23. And finally 4, so 4 squared is 16, 16 minus 4 is 12, 12 plus 17, that's exactly 29. You see, this polynomial is also an explanation or a pattern that these 4 numbers satisfy. So there are at least 2 good explanations for a pattern in these numbers. As a polynomial outputting these values, this polynomial is actually amazing. For 4 values, we always know by general interpolation theory that there will be a polynomial of degree 3 attaining these values. So it's really remarkable that we actually find a polynomial of degree 2 which can do this. And actually, so I don't really want to talk about this in this video. There's a deeper theoretical reason why this polynomial is so unreasonably good, but that's maybe for another story. This polynomial actually, one can even see that this is the best possible polynomial giving these values. Because, of course, there will be other polynomials having these values, right? You can cook up a polynomial of degree 16 having these values. It just gives you additional freedom to also fix other values before or later in the sequence. There are all sorts of other polynomials giving you these values, but the best you can expect by general theory is of degree 3, so that you can find one of degree 2 is absolutely remarkable. You can't go lower because the next lower degree would be degree 1, so a linear polynomial, and then this wouldn't have these values. If we only want to have a polynomial interpretation of these values, this is amazing and this cannot be beaten. There's no better polynomial giving these values. I'm already approaching a little bit how you can actually give the question, what is the pattern in these numbers? What is the next term? How you can give this an objective meaning? Because since there is no well-defined answer, you really need to put in some more constraints to give the question a sufficient meaning to have a well-defined answer. So in this setting, the best possible interpretation for this is you just ask for what's the simplest pattern. Don't give me any pattern satisfied by these numbers, but give me the simplest pattern. So now it's difficult. How do you measure? How do you compare the complexity of patterns? So the usual way is that you ask for the following. Give me a computer program which outputs an infinite list of numbers, just a while loop. And it just is a print command, outputting numbers every single step. So the program will run for as long until you interrupt it. And then you just demand that the first, in this case, 4 entries that this program should output should be these numbers. And now you can ask, what is the shortest computer program giving you these 4 numbers? And this is not yet really well defined because, first of all, a computer program needs to be written in some programming language. You know, if you write the same program in different languages, it will have different lengths typically. So you need to fix a programming language. And then there's even a little bit more of a problem because it could still happen that there are two different computer programs in this one programming language which have precisely the same length. You can always solve this. The one way how you could do this is you could just give your character set for the letters you use to write the program. You can give every character some index, some number, just like the nth letter in the alphabet. What is n? Unicode does this, for example. So you can attach to any letter a number, and then you can just lexicographically order all your programs of equal length. I mean, this is completely arbitrary, of course, and completely up to your choice to impose such means to differentiate between programs of the same length. But okay, so you need this to have a truly well-defined answer. But once all this is in place, you can really ask what is the unique, shortest, simplest, and smallest Unicode character codes program in lexicographical ordering which outputs these numbers. And then, of course, the sequence problem is solved by just letting the program run longer and use the next numbers which this program will output. How delicate this choice of the programming language is also exhibited in an excellent way by this sequence. Because imagine you use a programming language which has a great set of libraries and library functions for using prime numbers. Then what you can do is you can just figure out, hey, what is the number n such that the nth prime is 17? I must admit I actually don't know this offhand, but I will just call this alpha. Yeah, so let p be a function which could be existing in your libraries in this programming language, such that if you plug in alpha, you get the alphath prime number. So I pick alpha in such a way that it's 17. Then obviously, to get this sequence that I've just told you, right? So 17, 19, 23, and 29. So to get this sequence, all you have to do is just have to plug in, this is your program. There you go. So this is an extremely short program. And this is shorter than evaluating this polynomial, even though this polynomial is so short. On the other hand, imagine you have a programming language where you don't have library functions for the prime numbers, or you're not allowing any libraries. So maybe you're just allowed to use C++ plain. Then, of course, you can implement such functions. You can implement all sorts of functions like find the next prime or whatever. But this will take space, and this will make your program long. And so as soon as you have to implement anything in this direction, it will definitely be longer than this polynomial. So in all these programming languages, this will be shorter. So I think you see the dilemma. So even asking what is the simpler description depends. I mean, the answer is different. Now, let me show you an even maybe a more drastic example. So this is a difficult one to remember. It says 0, 1, 1, 2, 1, 4, 1, 3, 2. I would say it's pretty much impossible to guess what the pattern is. This is very difficult. So let me fill you in. Give me a number n. Consider this inverse. And I can ask, how many ways are there to write this number as the difference of two unit fractions? So that means I'm considering numbers m and l integers, at least one. And I ask, for a fixed n, how many ways are there to write this as this difference of unit fractions? And I claim that this counting problem outputs exactly these values. It's best to write a little computer program. We maybe want to do this anyway because we were talking about this thing like trying to find the shortest computer program outputting something. So let's try to write a short computer program solving this counting problem. It's not difficult. So for this, I will just rewrite this equation a little bit. This is equivalent to claiming that n is the same as 1 over m minus 1 over l. I've just inverted everything. Now I want a common denominator here. So this is the same as 1 over l divided by ml minus m divided by ml. Okay, and then I see that this is the same as m times l divided by l minus m. Okay, and this gives me the equation m times l is the same as l minus m times n. That's the same equation as before, I've just rephrased it. I'm learning some things here. So for example, I know that I learned that l should be bigger than m. If m is strictly bigger, then this would be negative. This would be a contradiction. So mean, you can already see this here, right? This would be negative then. Okay, and also L and M can't be equal because then this would be 0 and also is not the same as 1 over n. Okay, so I get this. Now I can try to figure out what is the largest possible value this side of the equation can have. And since m is at least 1, this thing is definitely at most L minus 1, right? I'm subtracting the smallest possible amount times n. And this is quite useful because now I can divide in this inequality by L. So I get m is less or equal than 1 minus 1 over L times n. And now if L is at least 2, I deduce from this then that m is smaller than n. Good, why is this useful? Well, it means that I can iterate through all values. I mean, m was at least 1, and now I know that it's at most n, so I can just run with a for loop through all numbers from 1 till n minus 1. And using m as a candidate number, I just have to figure out what L is. And since n is fixed, and I'm also fixing this n I'm running through, there can only be one L which possibly solves this. So, and this is easy to figure out. We can deduce this also from this equation here. So this equation, I'll just write it again here. So this was ml is the same as L minus m times n, and this is the same as ml is the same as ln minus mn, and this is the same as L times m minus n equals minus mn, and this tells me that L is the same as m times n divided by n minus m. Yeah, so here you go. Given n, I will just be looping through all values m between 1 and n. Then I know that at most one L can solve this. And this L would have to be this, but L has to be an integer. So I just need to check whether this fraction is actually an integer. So I just need to check whether m times n is divisible by n minus m. And then I just count this. So here's this little program. Note that this really does precisely what I claimed. So n is the value that we input. Then I'm just having a variable which will be counting how many solutions we find. I'm running from 1 till n, and this is written in Python. So this range means that this really will just be running till n minus 1. And then I'm just checking exactly this divisibility condition and add 1. I never actually compute what L is because that's irrelevant for this program. We just need to know how many solutions there are, not what they are. And this just outputs the first 10 values of this. So let's just do this. You get exactly the sequence which I just showed you. So great. This is probably not, I mean, this is for sure not the shortest program which outputs these values. I mean, there's in computer science, I mean, there's a lot of challenges among people. I think it's called code golfing, where people try to find the shortest program. So I don't claim that this is very well written from the viewpoint of being maximally short, but certainly this gives you a bound for how long a program would be outputting this sequence. Now, the fun thing with all this is that there is actually a completely different pattern in the same numbers. And this pattern works as follows. If I take the number n, I can consider the set of all divisors. I will be going through all possible choices of divisors d1 and d2. And then once I have them, once I have such a pair, d1, d2, I just ask, do they differ by precisely one prime? By differ, I don't mean that the difference of the numbers is a prime. I mean that in the unique prime factorization of these two, is d1 just d2 multiplied with one single prime factor, or the other way around? So I mean that multiplicatively, do these two just differ by one prime? I'm counting all the pairs where this is the case. So that sounds like a reasonably easy counting problem, and I've also implemented this, so let me show you. So this is what that code looks like. It looks a little bit, I mean, it looks longer now also because I wrote this very long comment above it. I'm just counting exactly what I've just explained to you, right? I mean, so again, we have some abstract counting variable. We start with 0. Then I'm running through all the divisors of n. So here I'm using a library function. Then I'm running through all the d1 and d2 in the product set of these divisors. And I'm just checking, is the fraction of them actually an integer at all? Because if that's not the case, then it can't be a prime. And then if it is, I compute it and I check whether it's actually just a single prime factor. The way I just explained it is like I was comparing whether d1 differs from d2 by multiplying with a prime or the other way around. I don't check it in these two directions here for the simple reason that I'm running through the entire product set. So I'll get every pair in both orderings anyway. I will also get all the diagonal entries where d1 equals d2, but since they don't differ by a prime, they won't be counted, so there's no overcounting. Yeah, so this is the program doing this, and now I can also run this. And yes, surprise, surprise. You see you get precisely the same numbers. So arguably, I think this second program, this is a little bit longer. So I think it has one more line of code here in comparison to this program. But You know, like, I mean, keep in mind, I didn't even try to optimize these programs for lengths, but I would say they are fairly close in lengths. I mean, I was using like a function here to use a product set. I mean, I could have avoided this at the cost of having a second for loop. I would say these programs are both, I mean, it's the same ballpark. These are close. Which one would you pick to continue the sequence? Of course, it could happen that maybe these are just the same counting problems, right? That we're using some maths and then figure out, okay, actually we're counting the same thing. So, but that's actually not the case. The counting problems are inequivalent, and I've also prepared something to show you that. So this is a little bit of a longer code. What this code offers for you is that it outputs not just the values of the two different programs, it also compares them. And when the values are the same, then the output will be in yellow, and otherwise it won't be marked in yellow. So here you see the first 9 entries for the first program and the second program, and you see they all agree. And this is in both times our mystery sequence. But now, instead of just doing this for the first 10 terms, I can do this for the first, let's say, 100 terms. And when I do that, you see that actually these sequences, they agree for even longer. But then at entry number 30, they actually differ by 1. This makes this example really super cool, because it means I could have given you 29 terms of this sequence and asked you to find the pattern. Both of the counting problems which I've just shown you are completely legit answers explaining this pattern, but then at term 30, actually the counting problems have a different solution. They are two different inequivalent counting problems. If you have these 29 terms and the task was to continue the sequence, then certainly, as you see here, you have a really good argument that 13 is a legit answer, just as would be 12. And then, to make the whole thing even more funny, afterwards the sequence continue to agree. Not for very long though, but you see you have to go to term 42 to have the next time a disagreement of 1, and then later there's also a disagreement of 2 at 60, a bigger difference. But all in all, you see these sequences stay very, very close. I mean, I can even show you more terms if you want. Let's do maybe 1000. So these counting problems, these two counting problems, they are very, very similar and yet different. So you see, as I go further down, still loads of agreement between all these terms. There's one more thing I want to show you. What about just doing the polynomial here? Because this was like a surprise in this first sequence which I showed you, like 17, 19, 23, 29. There was actually a quadratic polynomial which gave you the second explanation that this is not just prime starting from 17, but also the values of a rather simple polynomial. So what if we do the same thing here? And I've actually prepared this. This is this beast here. So I thought, because both sequences agree in the first 29 terms, I thought, okay, so let's just compute the polynomial which gives exactly these values for the first 29 terms. This will be a polynomial of degree 28, and here you have it. So there you see the term of order 28. The coefficients are horrible rational numbers. As you would expect, even if you have an integer-valued polynomial, the interpolation polynomial need not have integer coefficients. It usually has rational coefficients, and here you see that. And you see these are very, very complicated. This is a beast. That's also good to maybe see at this point. Just storing this polynomial will be longer than either of these two programs which I showed you, right? This is definitely shorter than storing this polynomial. This is shorter than storing this polynomial. In this case, it's completely clear that trying to somehow save this polynomial in a computer program will always produce a computer program which is longer than the other two candidates that we have. Differently from the prime sequence, which arguably which I showed you, 17, 19, 23, 29, where arguably, if you use a programming language without the library functions for prime numbers, the polynomial was the shortest solution. So, but here you see, no way. The polynomial is also bad for another reason. So here I gave you the values of these two programs, and you see that even though they differ sometimes, there's a lot of agreement. Even in the terms where the two sequences differ, the difference is not too big. You just see empirically, the sequences behave very similarly, and even if the values differ, they differ by not too much. I can actually also compare the sequence to the polynomial. Why not? I call this F3 here. But when you do that, you see why this polynomial is really not a good candidate, namely, as soon as we're getting out of the range where we have prescribed the values in our interpolation problem, you see that the values of the polynomial, these are the second ones here, right? So you see the first code output here, and then here you see the values of the polynomial, and they just explode, which is of course also precisely what you would expect. It's a polynomial of degree 28. It either looks like this or like this. The polynomial doesn't exhibit this behavior of having rather bounded values, which the interpretations of the other two codes gave. I would say also from this aesthetic point of view, the polynomial is really a really bad interpretation of a pattern in these numbers. One more thing about this, I didn't talk about one interpretation of how you can also come up with a pretty short program, and this is that you just hard code the values. What this means is if you just, for example, have a sequence where the first 4 terms are prescribed, nothing more, then what you can do is you can just program these 4 numbers, right? You can just write a program which is like, if the input is 1, then give me the first number. If the input is 2, give me the second number. If the input is 3, give me the third, and so on. And for everything else, return 20, whatever. The thing is, this is a really stupid program because you've just hard-coded the first so and so many values, and then you just return 20 for any other request that the program gets. But you must also always keep in mind that this is still a fairly short program. So it can happen that if somebody just gives you 4 values and says, please find a computer program outputting these 4 and use this to continue the sequence, it's very well possible that this program where you just hardcode these 4 values will be shorter than any other good interpretation. So certainly this could be the case for our programs here. And even if you just demand that these 4, whatever it is, I think these 9 values, if these first 9 values have to be correct, if you compare that to the character count I used in this program, if you have a programming language where you can write down very efficiently case-by-case differentiation, it's quite possible that just hard-coding these values is still shorter than this program up here. I mean, certainly this would be the case if I just give you the first 4 values. You can write this in a shorter program than this thing up here. This is also something you always have to keep in mind. Hard-coding the values is also a possible solution if you're just asking for a very short program. So I just showed you these 2 sequences where the first 29 terms agree and then there is a difference of 1. These are a very good example showing you that continue the sequence problems don't have a unique solution. But let me show you an even wilder example. Take 2 divided by 2 to the 1 over n minus 1 and now round this up. Yeah, so by these square brackets where the limits are missing on the lower end, I mean, round up the number. So in computer science lingo, this would be taking the ceiling of the number. And the other sequence is you round down. It's 2 times n divided by logarithm of 2. And then you take the floor, or you round down. Again, you get 2 sequences. You have very simple formulas describing these 2 sequences. You can write very simple computer programs outputting them. But the agreement of values of these 2 sequences is absolutely wild. So let me actually show you.
La 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 la. Waiting music. La 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 la.
So this is code evaluating these 2 sequences. So let me just quickly show you again these sequences. So here we have the first sequence. This is 2 divided by 2 over 1 over n minus 1. And then we round up, take the ceiling. And then here we have the second sequence, 2 times n divided by logarithm 2, and we round down. Sequence 1 and sequence 2. And now I'll just be evaluating this in the range from 1 to 100. And it's the same thing as before. So you see the value of the first sequence is the first number here, and then the value of the second sequence is the second number here. And again, if the values agree, they are marked in yellow. And you see they agree. And they already, at the 30th term, you still have total agreement. And they agree the entire time. And this is, I mean, this sequence is really, these sequences are really wild. I mean, let's just go up to 1000. Yeah, and you see, I mean, it goes on and on and on, and all these values, they agree. And we can even go, I mean, we can even go in completely different ranges. So let's maybe go into something like 10 million or so. I'll go in maybe steps of 10,000s. And even in this range, you see all of these values agree. So so we had this first sequence which I showed you, 17, 19, 23, 29. These were just 4 numbers which could either be interpreted as certain prime numbers or as values of a polynomial. So this was agreement of 4 terms, and then the 5th term would be different with both interpretations. Then we had this example where 2 sequences which are also different. differ for the first time at entry number 30. And here you see you can go really far up and all the terms agree. And to actually show you where you have the first disagreement, I put this here. So this, you have to go into this range to be able to see this. So I don't even want to spell out what this number is. Once we evaluate our two sequences in this range, you can actually find a difference. So here you see all these terms agree, and then there suddenly you have these two terms and they differ precisely by 1. This is actually the first time these two sequences are different. One can show that the sequences have infinitely many spots where they disagree, but otherwise they agree. And as you see here, it's just crazy, and this is the first time the sequences differ. What I want to do now is I want to explain how this comes about. So where does this effect come from? So let me just write down the generating function for the Bernoulli numbers. This is x divided by e to the x minus 1. So this is the same as the sum from k from 0 to infinity of bk times x to the k divided by k factorial. So bk is the kth Bernoulli number. I will not be using much of this. Just remember that this is the generating function of the Bernoulli numbers. You can use this as the definition for the Bernoulli numbers. And you also recognize that this expression looks pretty much like the expression here. So you see what I have to plug in for x is just 1 over n times logarithm of 2. And of course, when I want to plug this in, I also have to check whether this is within the radius of convergence. The radius of convergence will be determined by the first pole of this function. This function doesn't have a pole at 0, even though it might appear so, but this is a removable singularity because also the numerator is 0 at the origin. But then the first pole will actually be at the point when you plug in 2 pi I. So the radius of convergence will be 2 pi. And so you're safe plugging this into this identity. Also, this only gets really interesting as n increases. And so this gets closer and closer to the origin. So you're fine anyway. Now I will just plug this in and I get 1 over n times logarithm of 2 divided by. And now here this becomes precisely 2 to the 1 over n minus 1. So we're really approaching this term which we want to study. So the first terms of this are 1 minus x divided by 2 plus a 12 times x squared and then plus something of fourth order. So these are just the first terms of this series up here. So I'll just use these and we can remember that this is already a fourth order term. So this allows you to actually control the error you're making. Plug this in here. So I get 1 minus and then this. So this is 1 over n times log 2 divided by 2 plus here I get 1 divided by 12 times n squared log 2 squared plus, and then here's something of order 4 in 1 over n. This term here was fourth order, but then I've plugged in this for x, so now this becomes 1 over n to the fourth. Now I just need to go back to the term I'm actually interested in, so I'll first multiply maybe by n. I'll do this step by step in order to avoid messing up. So multiply by n, I get 2 to the 1 over n minus 1 is the same as n times minus, this goes away, so log 2 divided by 2 plus 1 divided by 12n log 2 squared plus something. Now actually something of order 1 divided by n cubed because I multiplied by 1n. I need to get rid of the logarithm 2, so divide by log 2. This is n divided by log 2 minus 1/2 plus 1 divided 12n times log 2 plus something of cube order in 1 over n. And now multiply by 2 and then I have the expression I actually want. 2 to the 1 over n minus 1 is the same as, so okay, so everything multiplied by 2, 2n divided by log 2 minus everything multiplied by 2. So I get minus 1 plus log 2 divided by 6n plus, and then something of cube order in 1 over n. This gives us a better understanding of these two values, because in particular this tells us that as n increases, the difference between these two values, they should actually not be close to each other, but there should be a difference of 1. And this is actually good for the sequences which we want to compare, because here you round up, here you round down. So, I mean, if it weren't for this 1, if it would just were true that these two values would be getting very close to one another, then if you round 1 up and round 1 down, you actually expect that you get different values. They should just differ by 1. When you have two values that are very close to each other, and then you round up, you get the integer above, and you round down, you get the integer below. So you definitely get two different integers. What really lies behind the fact that these agree so often, even though you once round up and once round down, is that you have this minus 1 here. And then this gives you a good estimate for how close these get to be differing by 1. But of course, this doesn't mean that these sequences will, for sufficiently big n always agree, because you still have this rounding up and rounding down effect, which makes the behavior of this a little bit erratic, I would say. For more on this, I would recommend the paper The Sequence of Fractional Parts of Roots by Kevin O'Brien, which discusses exactly this function. Let's just have a look at the first page. You find here exactly the sequence which we've been discussing, and the analysis begins exactly as we've done it, using the expansion of this function in terms of Bernoulli numbers. But then right away here with lemma 7, you see a much closer, much more detailed analysis follows, which gives you a far deeper understanding of what's going on. So I can only recommend that. So let's do another interesting sequence. What about this one? 1, 3, 8. What's that? And that's easy, right? Because just think about the Fibonacci sequence. Fibonacci, this was 1, 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 5 plus 3 is 8, and then you just see it, 1, 3, 8. So it's clear. This sequence is just every second Fibonacci number. That's a pattern. But there is another pattern, maybe a more interesting pattern. I mean, I'm just giving you 3 numbers, right? It could be any pattern really. But so here's a more interesting pattern. So suppose I multiply 1 by 3, then of course this is 3, which is just 1 below a square, right? This is 4 minus 1. And I can multiply 1 times 8, which is 8, which is just 1 below a square, right? Because that's 1 below 9, so it's 3 squared minus 1. But I can also multiply 3 and 8, which is 24, which is just 1 below 25, which is 5 squared. So you see another pattern in these 3 numbers is that as soon as I multiply any 2 distinct ones of these, I get a number which is 1 below a square. Yeah, so I mean, if you go with the interpretation that these are every second Fibonacci number, then it's very easy to tell you what the next term is. But what's the next term if we go with this interpretation? If we just say, okay, yeah, it's you need to have the property that whenever you multiply 2 distinct terms of the sequence, you get a number which is 1 below a square. So what's the next number I can put here so that this property still holds? Now this is a lot harder, but actually this was figured out by Fermat. And Fermat found it's 1, 3, 8, and then the next term is 120. So very different from the Fibonacci interpretation. Let's quickly check this. I've already checked that these are all working. So now I need to check this. So 1 times 120, this is, okay, 120 is just 1 below 121, which is 11 squared. So 11 squared minus 1. 3 times 120, this is 360. And 360, so 20 squared is 400. 361 is just 19 squared minus 1, because that's 361. And then 8 times 120, this is 800 plus, so it's 960, which is just a little bit above 300, so 900, which is 30, so this is 31 squared minus 1. So it works. But you see, if you do this, for example, in a group and you ask like, hey, what's the next term? Every time somebody comes with a proposal what the next term could be, you have to do one more multiplication. So the effort to check whether a proposal for the next term is correct is actually growing linearly. For one term, there's nothing to check because we cannot take the product of any 2 distinct terms. For 1, 3, for 2 terms, you just have to do 1 multiplication. Now, once you additionally get the 8, these are fine. So you have to multiply 8 with 1, 8 with 3, so 2 multiplications. And then here for adding the 120, we had to do 3 multiplications. So for the next term, whatever it is, you'll have to do 4 multiplications. So already checking whether the next term is correct is getting linearly more complicated as far as the number of multiplications you have to do is concerned. So what is the next term? So what's interesting about this sequence is that the next term was actually found by Euler, the famous Euler. And I'll have to copy it because I wouldn't be able to memorize this. And it's 777,480 divided by 8,288,641. And yeah, I also did something crazy. Instead of continuing the sequence to the right, I've continued it to the left. And even more crazily, I picked a rational number to do so. Basically, I've probably changed the rules of the game a little bit here. This term was found by Euler, and I will not go through the verification that this really works, but as you multiply this with any of these numbers, you'll always find that you're just 1 below the square of, in this case now, a rational number. But so the same property basically holds. Now you might be wondering, why is this the next term, or the next term when continuing the sequence to the left? Well, it turns out, and this was proven by Baker and Davenport in 1969, that if you just have this sequence, which Fermat found, as I told you, there is no further term. There is no further integer term that you can add to this sequence. It just doesn't exist. There is a very good reason why what Euler added to this sequence is a rational number, because there is no further integer term in this sequence. And then even in 2019, Stoll proved that actually this is also the only thing you can do if you allow rational numbers. So even this sequence now, it cannot be continued any further using rational numbers. By the way, I hope this is obvious that this is smaller than 1, right? This is roughly 0.09, I believe. So this really should go to the left. Now, so what's interesting about this sequence is that it's, as I've just explained to you, basically impossible to continue it using the pattern we've chosen to an infinite sequence. I will not explain the argument of Baker and Davenport to you that you can't continue this using integers, but let me explain at least an argument to you why it's impossible to continue this sequence just using integers to an infinite sequence, having the same pattern. And this argument that I'll show you is actually better. Whenever you have three numbers, b1, b2, b3, let's say ascending, that as soon as you multiply any two distinct of these, you're just one below a square. Whenever you have any three such, it's impossible to continue this to an infinite sequence still having this property. That's a really nice argument, so let me just sketch what it is. So let's assume we can find another term. The next term, I'll call it n. So b1, b2, b3 satisfy the conditions, as we discussed, and n can be added to it. I will not be demanding that n directly has to be directly the next term. So n doesn't have to be the smallest next n also having this property. It could just be any n bigger than these, so that all these together have this property. So what is the property? Well, as soon as you multiply any two distinct of these, you're one below a square. So b1 times n is one below a square. I don't know what this square is, so I'll just call it x. So it's one below a square. b2 times n is one below a square. I don't know what that square is. I'll just call it y. b3n is just one below a square. I'll call it z. Now the idea to get to a contradiction is you just rewrite these equations as follows. So x squared is the same as b1n plus 1, y squared is the same as b2n plus 1, and z squared, I mean, this is pretty trivial, by the way, z squared, not cubed. And z squared is the same as b3n plus 1. And now I just multiply all these equations. And what do I get? I get x, y, z in brackets squared is the same as b1n plus 1, b2n plus 1, and b3n plus 1. And now I'll just give this a new name, maybe u, or I mean whatever. I'll just, the product of x, y, z gets a new name as a variable. And then I recognize that I'm actually getting the affine equation of an elliptic curve, because this is u squared, and then I have a polynomial in the variable n of degree 3. Should I spell it out? I mean, it's u squared is the same as b1n plus 1, b2n plus 1, and b3n plus 1. And okay, so at first this is just a cubic curve written in affine coordinates. In order to really to be a smooth cubic, I have to check whether this curve is smooth. But if you have an equation in this form, this is equivalent to checking that the roots of the polynomial on the right-hand side, that they are distinct. But so you have to interpret this right-hand side as a polynomial in the variable n and check whether the roots are distinct. But the roots will just be like a minus 1 over bi for these bi. And because these terms in the sequence were assumed to be ascending, they definitely are distinct. So we have distinct roots, so this defines a smooth elliptic curve, or well, if there's a rational point. But well, I mean, so every such n gives even an integral point. But now there's the famous theorem of Siegel, which says that any curve of genus at least 1 in an integral affine model has only finitely many integral points. So this means that this curve, whatever b1, b2, b3 are, will only have finitely many pairs un of integers solving it. But if there's only finitely many such pairs, then this also means that there are only finitely many possible values for n, and this means that there are only finitely many possible values for this n. But under the assumption that we can continue these b1, b2, b3 to an infinite sequence, then of course I get infinitely many terms, and all of which I can choose for the value n, forcing that there would have to be an infinite amount of integer solutions to these equations, which we've just ruled out. So this argument shows that it's impossible for any triple, so here in particular I could take now 1, 3, and 8 here, then this shows that there can only be finitely many terms how I can prolong the sequence. So Baker and Davenport showed that 120 is actually the only further solution that you can put if you start with 1, 3, and 8. I will not explain the argument of Baker and Davenport. So it does actually not use elliptic curves. They use a different technique. And you can't use this technique at all for ruling out that there would be an infinite sequence of rational numbers, because an elliptic curve can have infinitely many rational points. But like I said, so it's also known that you can't continue this sequence further. So what's interesting about this sequence is that even though you perfectly understand what the pattern was, right? The pattern is multiplying any two distinct terms is just a value 1 below a square. Even though that's completely clear and we have agreed on this, it means that it's by no means clear, even though this is an easy rule, to find out what the next term of the sequence is. And in particular, there might not be a next term. It might not exist. And by the way, so there are many more sequences having this type, right? I mean, I just get these terms because I started with 1 and then just picked the next bigger number, which has this property, which is 3. But you can just start with any two other numbers. And so there are many more sequences having these properties. I believe, however, that we don't know any sequence which has more than 6 terms satisfying these assumptions. So, yeah, so this is also something that can happen. For more of this, I can recommend the paper by Baker and Davenport, which is quite old by now. You see, it's from 1968. And there's also the paper by Stoll, which is freely available on the archive. You can have a look at it, and it frames the problem slightly differently, but it's essentially what we've discussed. You might recognize this type of equation here. Instead of -1, you have a +1 here, but it's of course discussing the same problem. Yeah, so check out these papers. I can only recommend them.